It's time to talk some inverses, and especially inverses when we're looking at graphing on a coordinate plane. So an inverse is a relation obtained by exchanging the x and the y coordinates of all the points, or by exchanging the x and y variables in an equation. And I'll show you what I mean. So for example, if I have a relation, if I have these coordinates right here, 5, 1, 6, 2, and negative 4, 8. If I wanted to graph, well, let me graph those first. So I got 5, 1, 6, 2, and negative 4, 8. And if I wanted to graph their inverses, I would just flip-flop the x and the y, just like I do to all these guys right here. So 5, 1 would become 1, 5. 6, 2 would become 2, 6. And 8, negative 4 would be, negative 4, 8 would become 8, negative 4. So take a look at those. I want you to start seeing a pattern. Try to tell if there's any type of reflection in this case. You starting to see like a little bit of a reflection? Okay, so keep that in your mind as we look through some more graphs. So here's another one, but now it's an equation. So I have a relation y equals x squared. So if I wanted to write its inverse, all I would do is exchange the y and the x. So now I have x equals y squared. So if I graph y equals x squared, that's at 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. It's our parabola, right? A quadratic. Just like that. If I wanted to graph its inverse, well, then I'd have to get the y by itself. And how do I get the y by itself in this case? Yeah, I'd have to take the square root of both sides. And anytime I do that, I have to put plus or minus out front. So if I know my radical x, so the graph of the positive radical x would be at 0, 0, and then going to 1, 1, and then 4, 2, and then 9, 3, all of our perfect squares. And if I graphed the negative radical x, now it's reflected over the x-axis. So it starts at 0, 0, now 1, negative 1, and 4, negative 2, and 9, negative 3. Just like that. So take a look at those two. Let's go back to our points, and now go back to these two. Are we noticing any type of reflection yet? Okay, and if not, start thinking about where you could draw a line to make them reflected. We're going to look here in just a second. So the notation for the inverse of function of f of x is f negative 1 of x. All right, so just be careful. So normally we call a function, we give it a name, and then we say what it's made up of, f of x. Or I could say, g of x. And then its inverse, we throw a little exponent of negative 1 onto the f. Now be careful, that does not mean it's the reciprocal of f of x, right? I know we're getting a negative exponents and we think, oh yeah, it's the reciprocal. You just flip it with a negative. No, this is technically not a negative exponent. This is just a term. It's a name. We're saying this stands for inverse. This stands for the inverse of a function. It's not an exponent. Okay, so get that out of your head. Don't apply that rule to inverses of functions. So this is just a name. So for example, let's just even go back to this guy. So what happens is if this is my function, f of x is x squared, its inverse would be, well, I'd flip-flop them just like I did, and I'd solve for y, and I'd use this, except now I'd say f negative 1 of x, the inverse is plus or minus radical x. So I still have to get them both equal to y before I can write the inverse, because they have to be made up of x's. So in this case, here's the function, here's its inverse. All right, so now I have another one. Let's take a look at one more here. So here's my relation, y equals x cubed. All right, let's write it in function notation first of all. So I'd say f of x. Let's give it a different name just so we get used to giving them different names. Let's call this guy p of x. Yeah, cool. All right, equals x cubed. So its inverse would mean we replace the x and the y. So basically, I just exchange their spots. So down here. And then I have to get the y by itself. So I'd have to take the y to the 1/3 power, which means I'd take the x to the 1/3 power, or I could take it to the third root, I guess. And I'd get y equals x to the 1/3. And if I want to write that in function notation, I would say I called this guy p. I'd say p negative 1 of x equals x to the 1/3 power. Now, if I graph both those guys, in this case, yeah, I might have to look at my calculator to graph these ones. So I'm going to graph x to the third and x to the 1/3, so 1 divided by 3. Remember, put it in parentheses if you don't have this nice superscript right here. And remember, if they don't show up very well, Zoom Standard's a good one to go to right away, or maybe even Zoom Fit. I'm going to go to Zoom Standard first. So there's x cubed, and there's x to the 1/3. Ooh, those are kind of fancy. So let's go ahead and try to graph those now. So this won't be very exact, but the x cubed is looking like that, something like that. And the x to the 1/3 is more so like, kind of like that. So I'm pretty close, not exact. Are we starting to see where that line of reflection's at? Can we tell yet? So let's go back and look at all those graphs. Try to think of drawing a line that would make like a mirror to reflect those graphs. Are we starting to see where it's at? Hopefully we can tell it's this line right here. There's like a mirror right there. Same thing right here. There's a mirror right there. Right? Same thing right here. There's a mirror right there. Well, what line is that? Remember, if it goes through like -1, 1, -2, -2, -3, -3, 1, 1, 2, 2, the y's and the x's are the same, so that's our y equals x equation. So the graph of the inverse is a reflection of the graph of our regular function over this line. So they're just a reflection over that line. So let's just glance at those again. So I drew my y equals x. They're not perfect, but it's just a reflection. So the blue right here was the function, and its inverse was the red. So these two got reflected here, and this blue got reflected here. Same thing, reflection over the y equals x. So some inverses are functions, some are not. How can we tell by looking at a graph of f of x if its inverse will be a function? Okay, well, let's go back to this guy, for example. So this blue one is a function, right? It passes the vertical line test. Is the red one a function as well? Is its inverse a function? Yeah, if I do the vertical line test, it works as well. So this would be if they're both functions. And if they're both functions, both a function and its inverse, if they're both functions, we call the normal function a one-to-one function. A one-to-one function. So for example, in that one we just looked at, this guy is a one-to-one function. X cubed is a one-to-one function because its inverse is a function. Well, if I went back to x squared, all right, so now if we look, the original is a function, but is its inverse a function? No, it is not. If I try drawing a vertical line, doesn't pass. So this one is not one-to-one. And can I tell the difference? What would be a quick trick to do that? If I notice the blue one passed a vertical line test, but if we notice as well, I know I'm getting a lot of stuff here, the blue one also passes a horizontal line test, and its inverse was a function. So this was one-to-one. But if I look back at x squared, it passed the vertical line test, my original, right, these green lines, but it did not pass a horizontal line test, which means its inverse is not a function. So not one-to-one. So we should notice that if we use, so we should notice that your function needs to pass its vertical line test to be a function, first of all, and it also needs to pass a horizontal line test in order for it to be one-to-one. Okay, so if it passes the vertical, it's a function, right? If it passes the vertical and the horizontal, then I know its inverse is also a function. So it's got to do both in order to be one-to-one. So let's do one more and let's decide. So if I graph this guy, I have a, let's give it a name. Let's go f of x equals, I'm going to flip-flop these. So I have a y-intercept of 6, a rise of 3, run of 1. I could go down 3, left 1, so it's like this. Okay, so it passes the vertical line test. It also passes the horizontal line test. So I would say this guy is one-to-one already. Its inverse should be a function. And if I wanted to write its inverse, well, first of all, I flip-flop the x and the y, so I'd have x equals 6 plus 3y, and then I solve for y. So I got to subtract my 6 over, and then divide by 3. So I'd have y equals 1/3 x minus 2. And if I wrote that in function notation, it would be the inverse, so f to the negative 1 of x equals 1/3 x minus 2. And let's go ahead and graph that. So negative 2, up 1, right 3, up 1, right 3. I go down 1, left 3 as well. Down 1, left 3 as well. So is that a function? Yep, passes the vertical line test. We already knew it was going to be, and it should mirror the y equals x just like that. Beautiful. So first you'll get practice at just changing a function into an inverse. So what happens is we have to rewrite this with y instead. So y equals 2x minus 5, or plus 5. And then to do its inverse, I have to flip-flop the x and the y. So I'd say x equals 2y plus 5, and then we need to solve for y. So we subtract our 5 over and divide by 2. So in this case, I'd have 1/2 x minus 5 halves. And this would be our inverse. So f to the negative 1 of x would be 1/2 x minus 5 over 2. Okay, so rewrite it with y. First of all, replace that f of x with y, flip-flop them, and then solve for y before you replace to write your function notation for the inverse. Okay, I'll do one more really quickly so we see it. So I rewrite, flip-flop the spots. So I'd have x equals 3y squared plus 1. Subtract my 1 over. Divide by 3. And then two options. I could either take it to the 1/2 power, or I could square root the whole thing. So I'm going to square root because it's going to end up being plus or minus. So y would equal plus or minus radical x minus 1 over 3. So plus or minus radical x minus 1 over 3. There we go.